In today's podcast, we're going to look at the geometry of molecules, what shapes they have, and those are governed by something known as VSEPR theory. VSEPR stands for valence shell electron pair repulsion theory, which is a huge mouthful, but here's basically what it means. If you've got electron pairs around a central atom, they're going to repel each other, and they're going to repel each other to the greatest possible distance they can. And it turns out that if you have an unshared pair, sometimes also known as a lone pair, that pair repels more strongly than when electron pairs are shared. So we're going to look at a bunch of different examples and see what shape each of these things makes based on their electron pair arrangement. So what I want you to do now is make sure you have a molecular model kit, and in that molecular model kit, I want you to find the list that shows you what color each element is. Depending on which kit you have, it might be inside the lid or on top of the lid. Look around and locate that. It's printed here in case you can't find it anywhere in your kit. Then I also want you to notice that we have different kinds of bonds in the kit. The shorter ones that don't bend much are the ones we use when we just want to single bond something, when we want to show one shared electron pair. The longer ones that bend easily, those are what we would use if we want to show a double bond or a triple bond in a compound. So what we're going to do is we're going to kind of go through a whole bunch of examples, but I want you to have this table in your notebook, and we're going to fill it in as we go along. So if you can just pause this video and get this in your notebook. You might want to turn your notebook sideways because you're going to need, especially in this example space, you're going to need enough space to draw a sketch of the molecule that you build. All right, so let's start with methane and figure out what kind of shape it would have. So to determine the shape of a molecule, the first thing we have to do is figure out how many shared electron pairs there are around the central atom. And the only way you can do that is to draw the dot structure. So I'll go through that with you. If you can also pause and practice writing the dot structure if you feel like you need some more practice with that. So carbon has 4 valence electrons, and hydrogen has 1. So that's 4 times 1. So we have 8 valence electrons to deal with. So I'll put carbon in the center. Then I'm going to join each hydrogen with a single bond. That's 2, 4, 6, 8 electrons taken care of. So that's the dot structure of CH4, also known as methane. And now what I'd like you to do is go ahead and take your model kit and build a model of this atom. So get a carbon atom, a black one, and 4 white ones, and build that model. If you want to pause while you do that, go right ahead. So I'm going to switch into a virtual modeling kit. And when you've built your CH4, this is what it should look like. Now you notice it's not a flat molecule like when we drew it on the page with the dot structure. When all of these electron pairs push themselves to the greatest possible distance, we get this shape. This shape is called a tetrahedron. Now don't worry about writing all this down right now. We will put it into our table after we've looked at it. So this is a tetrahedral molecule. Maybe you remember in geometry the shape tetrahedron. If we join the hydrogen atoms on each side of this molecule, we get a 4-sided figure that has a triangle on each side, and that's called a tetrahedron, and that's why this is called a tetrahedral molecule. If we were to measure the angle between each one of these bonds, right in here, it's 109.5 degrees. It's called the tetrahedral angle. So let's go back to our chart and put that in. So this is what the molecule looks like, and here's its original dot structure. The shape of this is called tetrahedral, and it has a bond angle of 109.5 degrees. So pause if you need to get all this down. And then I'm going to move on to the next one. The next one we're going to look at is ammonia, NH3. So nitrogen has 5 valence electrons, and hydrogen has 3. Pardon me, each hydrogen has 1. There are three hydrogens. So that's a total of 8 valence electrons. So first we put nitrogen in the center, join all the hydrogens with single bonds. So we have 3 hydrogens. So that's 2, 4, 6 electrons taken care of. And then we need to put a lone pair up here, or a non-bonded pair, so that the nitrogen has an octet. Now if we look at that, if we build that in our model kit, you're going to take a blue nitrogen and 3 hydrogens. Some of the nitrogens in the model kit have 4 holes. They should really only have 3, but only use 3 holes to make the ammonia. And I'm going to switch to my virtual model kit while you build your model. And here's what ammonia should look like when you've built it. Now notice again, it's not a flat molecule. Okay? It looks like a little pyramid. Okay? And we call this molecule, we call this shape trigonal pyramidal, because it's a triangle, it has a triangle base, and it's a pyramid. Now what about the bond angle? Again, don't worry about writing all this down. We'll put it into the table when we're done. But let's look at something for a minute. Let's show where the lone pair is. Okay, so remember that if we look at the dot structure, there's that lone pair of electrons that has to be arranged around the central atom too. So you've got 3 shared pairs, okay, and then you've got 1 unshared pair, and that unshared pair also repels just like these. So it looks a lot like the bottom of the tetrahedral molecule. But remember that this lone pair repels more strongly, so it pushes all these shared pairs together slightly more. Okay? And so what we end up with is a bond angle that's slightly smaller. It's 107 degrees instead of the 109.5. So if we move back to our table, okay, the shape of this molecule is trigonal pyramidal, and the bond angle again is 107 degrees. Now you might want to make a note somewhere that because you've got an unshared pair, it pushes the shared pairs together more closely, and so therefore the bond angle is smaller than when you have all shared pairs. Okay, now on to another molecule, water. Okay, each hydrogen has 1 electron and oxygen has 6, so we've got 8 to deal with. Now obviously we know that hydrogen can only ever make 1 bond, so oxygen's going to go in the middle. We'll join 2 hydrogens, so that's 2, 4, 6, 8. So in this case we have 2 shared pairs and 2 unshared pairs. Okay, so we've still got 4 things arranged around that central atom, just like we did in the last 2 molecules, but now we've got 2 unshared pairs. So you might be seeing that those are going to push even tighter. That bond angle between here and here is going to be even a little smaller. And let's go ahead and build that. We'll switch to my virtual model kit. And here's what water should look like once you've built it. Now remember, the reason that this is not a flat molecule is because we do have those 2 unshared pairs. So let's add the unshared pair here so that we can, unshared pairs, so we can see what's going on. It's a little hard to see with this model kit. I kind of like it if it showed 2 electrons instead of a blob, but obviously we've got this area of shared electrons, unshared electrons here, another one here, and you can see it's just kind of like the tetrahedron in the way that they're arranged from each other, but because these are unshared pairs, they push the 2 hydrogens closer together, these 2 shared pairs, so this bond angle ends up being 104.5. So let's add all that to our table. Okay, so here's the water molecule. The name of this shape is just bent, okay, because you can see that it's not a linear molecule, it's bent. And the bond angle between those two oxygen-hydrogen bonds is 104.5. Okay, we have 3 more that we're going to look at. We're going to look at the carbonate ion now. And this is probably a good dot structure for you to practice. So if you want to pause and try and do it on your own, that might be a good idea. So we've got carbon, which has 4 valence electrons. And we have 3 oxygens, and each of those has 6. And then this 2 minus means we need to add 2 more electrons to that whole structure. So I have 18, 24. 24 total valence electrons to deal with. So I start out with carbon in the center, join all the oxygens with single bonds. Yeah, so I've got 2, 4, 6, and I start distributing 8, 10, 12, 14, 16, 18, 20, 22, 24. So I've run out of electrons, but the carbon only has 6 electrons around it. So that means I need to make a double bond. Just get an eraser here to move some of these. Oops. Get an eraser here so I can move a pair of electrons. I'm going to move these electrons right here. And change and add a double bond. Okay. So now this carbon has 8 electrons around it. This oxygen has 8. They've all got 8. But remember, when we have a polyatomic ion, we need to put square brackets around it and give it a charge. Okay, so let's take a look now. Go ahead and build that model. All right, with a carbon atom and 3 oxygens. And I'll switch to my model kit. And we're looking at the carbonate ion. And here's what you have. Okay, notice it is a completely flat molecule. Okay, we have this double bond here and 2 single bonds. Okay, we've got 3 shared charge centers on the central atom. Okay, so when they push themselves to the greatest possible distance, that's 120 degrees. So it's a flat molecule. It's called trigonal planar because it makes a triangle, but it's flat. So it's all in one plane, trigonal planar. So let's go back and put that in our table. And the name of this again is trigonal planar. And the bond angles are all 120 degrees. Okay. 2 more molecule shapes to look at. Next one we're going to look at is ozone, O3. Now, each oxygen has 6 valence electrons, so that gives us 18 electrons to work with. So I'm going to start by joining all 3 oxygens to each other. Well, that's 4 electrons, 6, 8, 10, 12, 14, 16, and 18. I realize that I'm 1 short, so that means I'm going to need a double bond. So let me grab my eraser here and move that pair, get my pen back, and I put a double bond there. Now this oxygen has 8 valence electrons. This one has 8, and this one has 8. So everybody's happy. So we have 1 double bond, 1 single bond, and a lone pair of electrons on the central atom. So let's take a look at what that looks like with our model. Let's go ahead and build that. Now, when you build it, you're going to need to use an atom besides oxygen. You need to use some besides the red atoms, because this is kind of unusual. Oxygen here is making 3 bonds, and it generally makes 2, but in this is kind of an exception to that. So you might want to just use a carbon atom, one of the black balls here, to do this model. My virtual model kit lets me do some things that you can't do with yours, but let's have a look at what. So here's a model of ozone in my virtual modeling kit, and notice that I do have a double bond in there. It's just a little hard to see when you turn it this way, and because oxygen's not behaving as it normally does in a lot of compounds, I can't really turn on the lone pairs here. But remember that there is one lone pair right up here, so you've got basically 3 charge centers on the central atom, so they're all pushing each other. But then one of those is an unshared pair, so it pushes these 2 closer together. And so instead of having a 120-degree angle in here like you did with the carbonate ion, you're going to have a 116-degree angle in ozone. Okay? This is also a bent molecule, but it's a different kind of bent molecule than water because there's only 3 charge centers on the central atom instead of 4. So if we go back to our table, so this is also a bent molecule, but its bond angle is 116 degrees. All right, one more molecule to look at, carbon dioxide. Now, I'd also like you to practice this dot structure. If you're having any trouble with dot structures at all, it's a good one to practice. So you can pause and do it or just follow along. So carbon has 4 valence electrons, and each oxygen has 6. So that's 12 plus 4 is 16 valence electrons to work with. So I take the carbon and I join it with single bonds to the oxygens. Then I start distributing electrons. So I've got 2, 4, 6, 8, 10, 12, 14, 16, and then I've run out. And in fact, I'm missing 2 pairs because the carbon only has 4 valence electrons around it. So that means I need to make 2 double bonds. And I'm going to do that by moving 1 pair off of each oxygen. And making a double bond on either side of the carbon. So now I have 2 charge centers on the central atom, 2 areas where electrons are shared. Now they're not shared pairs, obviously there's 4 electrons in each space. They're going to repel each other to the greatest possible distance. Go ahead and build that molecule, and then I will pull up my virtual model. Here's carbon dioxide. So you have 2 double bonds, okay? And they're going to push each other to the greatest possible distance. So it's going to be a completely flat and straight molecule. It's a linear molecule, and the bond angle is 180 degrees. So let's add that to our chart. This is a linear molecule, and the bond angle here is 180 degrees. Okay. Now, take the time now, if you haven't already, to really make sure that you've filled out everything in this chart, that you have a good sketch to remember what the molecules look like. If you're not very good at sketching and you want to go ahead and print this page out from the PowerPoint on the website, go ahead, okay? Because that it might be helpful to you to have the actual pictures. Okay, but you are going to need to know all of these shapes and all of these bond angles and be able to predict them from a dot structure. The way to do that is to know how many shared and unshared charge centers are on the central atom, and that dictates the shape. There's only 6 types to know, so it's not really that many. So here's a summary. Okay, we talked about this at the beginning. Let's go through it again. So electron pairs push each other, and they're always going to push each other to the greatest distance they can get from each other. Unshared pairs will repel more strongly than shared pairs. And like I just said, you have to memorize the shapes and the bond angles for these geometries. Now, these are only the ones that obey the octet rule. If you go further in chemistry, there are a lot of molecules where the geometry is much more complex, and there are some atoms that can be deficient in their octet, some that can exceed the octet rule, but we're only going to look at the ones that obey the octet rule. And of course, we have to end with a chemistry joke, and this one totally cracked me up, so I thought I'd share it.